Hi, welcome to the first video of the series JAX 101. In this series, I will try to present the JAX library, explain how to get started with it, and how to get started with JIT compilation, which is JAX's main selling point. But before getting to the code, I would like to present let's say, in an overview, the main components of the JAX stack. So, what is JAX? JAX is a scientific computing library developed by Google, and you can use it for everything that you want. I mean, it can be machine learning, physics, weather prediction, everything. Like, as long as it is scientific computing, go with it. So, at its core, what makes JAX really efficient is what we call the XLA compiler. XLA stands for Accelerated Linear Algebra, and it's a device-agnostic compiler that is made to optimize your code depending on what you are trying to do, like whether be it running your code on a GPU, a TPU, a CPU, any kind of accelerator. XLA is there to take your code and then make it efficient, and it will do it well. But you won't be working with the compiler. What you are more interested into is this part of this figure. Like, while working with JAX, you will mainly interact with it using the high-level JAX module and the JAX.numpy module. So, the JAX.numpy module is the module that provides all the array manipulation methods that you need. Like, I mean, if you want to create an array or apply some mathematical functions on it, everything. It's the equivalent of NumPy. That's why if you are familiar with NumPy, you are already familiar with JAX. You only need to get familiar with the function transformations that JAX provide. On the other hand, JAX also provide a module that is called LAX. What is LAX? LAX is the low-level API sitting between the high-level API that you will use in this part and the XLA compiler. And all the operations that JAX.numpy provides are written using the primitives, that is to say, the functions that the LAX module provides. So if you like to create a custom operation that is not built into the JAX library, you can simply use everything provided by LAX to do so. And then finally, there is a small bonus that is called Palace. What is Palace? Palace is a kernel language. For those of you who are familiar with deep learning optimization and things like CUDA programming or Triton, so let's say that Palace is the equivalent of Triton but for JAX. And this one also is made device agnostic, but you can apply some device specific configurations to get the maximum benefit of your hardware. But if you would like to get started with Palace, let me know about it, and then surely I will make a video about how to use Palace for your research workflow. Well, now let's get to the code. Before starting to write the code, we first need to install JAX. To do so, I'm going to use UV, the package manager in my case. So if I would like to install JAX, I will simply use UV add JAX, and that's it. The reason why I'm using UV is because it's fast, first of all, and then it's quite recommended to use a package manager in virtual environments while working with Python. That way your project will be more maintainable and you won't have conflicts with packages versions. So, but it's the same thing. You could still use pipe and then pipe install JAX, or if you want the additional CUDA capabilities, JAX.CUDA 12 or 13 if you are using the latest NVIDIA GPUs, or if you are working with TPUs, JAX TPU, and that's it. Now, after installing the required libraries, you can import the JAX main module, the JAX.numpy module as JNP, and then we'll also import the NumPy module. Here it's just for convenience to show the equivalence between the two APIs. You will see that whatever you can do with NumPy, you can do it with jax.numpy. So we run this cell, and then we'll start with some basic array creation. So let's start with a list, let's say a dummy list with values ranging from 1 to 4. And then this list, we can simply pass it to the method gnpay.array, and it will return a JAX array. As you can see, these are our values, and the array has the data type of int32 because we only have integers in this list. And in the same spirit, you can create a JAX array from a NumPy array. The thing is that whatever you can do with a NumPy array, I mean, if you like to create a NumPy array, JAX is following the same logic. But the thing is that JAX arrays can be created from NumPy arrays too. So you can pass something, either a list, a tuple, or a NumPy array. Whatever it is, it will pass and JAX will convert it into its own arrays. That's the philosophy, nothing fancy. But then you could also create arrays using NumPy specific functions, something like array range, line space, or even some mathematical operations like the cosine. And if we run this cell, we get the following output. So as expected, array range will produce values ranging from 0 to 9. So line space will produce an array of floating values. And then here we apply the cosine, and that's all. And if we use the same logic with JAX, we get exactly the same thing. I mean, values ranging from 0 to 9. Here with line space, we get some subtle differences. For instance, here it ends with a 3, but here it ends with a 2. So these ones are errors related to floating point operations with machines. So from one library to the other one, it's the same thing, but errors are quite minimal. And we can't quite frankly call this an error. So it's more related to the implementation of the library. Because in the end, if we try to run numpy.allClose to check whether or not the two arrays are equivalent, we will see that our JAX array here, y and ynp, are equal at all points. So that is to say that it's absolutely equivalent. Whatever you can do with NumPy, you can just use JAX.NumPy and do it. All functions are available. It's like if you try to do some, let's say, linear algebra specific methods, like let's say, I don't know, eigenvectors, eigenvalues. As you can see, this method is defined here. The same method can be found in jnp.linearalgebra. That's agent. As you can see, they are all equivalent. There is no specific changes related to JAX or whatever it is. That's why your familiarity with NumPy will greatly benefit you while working with JAX. Well, now let's get to the crux of the matter. That is to say, JIT compilation and JaxPr. But before showing you some code, I would like to discuss something. That is the compilation process. And this figure here will help us. So, what you have to understand is that when you are at this level, writing your Python code, your fancy mathematical expressions, your Python code is just a way to interface with the XLA compiler that is sitting right here, just between your Python code and your hardware. You won't directly talk to the hardware. And the thing is that when you use the JIT function transformation, what JAX will do in the first time is that it will transform your function into what we call a JaxPr, which means JAX expression. And a JaxPr is just an intermediate representation. If you are familiar with languages like C# or Java, so it's like the bytecode that is generated before forwarding it to the virtual machine. So your JaxPr will be transformed into what we call HLO, which is another intermediate representation that the XLA compiler will use in order to optimize it and then generate code that is specific to your hardware. So whether you are targeting a CPU, a GPU from AMD, or a GPU from NVIDIA, or a TPU from Google, you only have to write code once, and then XLA will take care of everything, optimize it, and then leverage your hardware as much as possible in order to get the maximum benefit from it. That's the whole philosophy behind compiler-driven optimization. But I've been talking about code optimization made by the XLA compiler here and there. Let's clearly see what's the matter with this simple example. Let's say that we would like to compute the following expression. That is to say that we have three variables, x, y, and z, and we would like to compute x plus y and then scale the whole result with the z array. What we will do normally is to first of all compute the sum between these two arrays and then store the result in an intermediate variable. Here, let's call it temp. And then the result of, let's say, the content of temp will later on be scaled by the z array, and then we obtain our final output. This is normal. Let's say that this is the most basic flow of information for this use case. But what we have to understand is that while writing this kind of code, that is to say doing mathematical computation, is that there is some kind of IO pressure that is made on the memory, because in order to get the value from the X array and then the Y array, we have to read 2 times from the memory, and then later on to store this result we have to write 1 time back to the memory, and then to get the final output we have to repeat the same pattern, read 2 times and then write back once. What we have to understand is that in order to make our operations really fast, we have to reduce all the operations made with the memory, because if we are using too much, if we are performing too much input-output operations, there is the bottleneck. But if we reduce them, everything is quite fast. And this is what we try to fix by using operation fusion. What is fusion? Fusion is what we have in this figure just next to what we had. So operation fusion performs the following way. That is to say that we still have the same operation to perform, x plus y all scaled by z, by instead of having this intermediate variable that will sit somewhere here that will store the result of x plus y, we do everything in one go. That is to say, x plus y directly scaled by z, no need to store it. And this is what we call operation fusion. That is to say, combine all the operations that can be done in one go and do them in order to minimize the number of input-output operations regarding with respect to the memory. And if you look closely, in this example, we only read the memory 3 times and then write back once. But in the previous example, we were reading 4 times and then writing 2 times. That is to say 6 operations, and then here we fell back to only 4 of them. Now let's get back to the code, where we will define our previous example in terms of JAX operations. To do so, we define a function called operation, which takes as input 3 arrays, a, b, and c, and then we compute the sum a plus b, and then scale everything by c. And in order to visualize the JaxPr created by JAX for a given operation, we can make use of the function called makeJaxPr provided by JAX, and also provide input variables that JAX will use in order to evaluate our provided function and then create its JaxPr. And what's the function makeJaxPr returns is what we call a closed JaxPr object. And this function, this closed JaxPr object, can be transformed into a string in order to be visualized by simply converting it into a string. And if we print it, we obtain the following representation. That is to say that it starts with lambda like saying that we are defining a function, and it reads like assembly or WebAssembly if you are familiar with it. So here we have the declaration, the input variables with let. We have our first parameter, a, which is of type int32. There is the b parameter of type float32, and c, which is also float32. Remember that the first parameter is of type integer, because x here that we defined was created using array range, and array range returns integers. Reason why the first operation in our function is to convert the type of a here into float 32, and this converted array will be stored into the d variable, and then now we can proceed to the sum. We compute d plus b at this level, and remember that the d variable here is just a but converted to float type, and then we store the result of this sum into the e variable, and then e is multiplied by c, and the result of this multiplication is stored into f, and then we simply return the f variable, which will be our output. So this is what JaxPr is doing. As you can see, it reads like the figure that we saw previously. Now let's take a closer look at JIT compilation and understand what's going on behind the scene. To do so, we will create an optimized version of our operation using jax.jit that will return an object of type JIT_wrap. And what you have to understand is that our optimized function here, fastFN, can be used as a normal callable function, as here it is defined with operation, but it has some additional benefits. Let's say that given the transformations operated by the JIT function, now we can lower it, and by providing some sample inputs, we can compile it and return a text representation of this function that we will write back into a file. And now we can inspect the generated HLO by JAX. There is a bunch of metadata up above, but the most interesting part is here down. This is where things are happening. To understand what the XLA compiler did to our operation, we have to take into account this first part that has been defined called fused computation here above, and then there is the entry module where this fused computation will be invoked. As you can see, the entry module has three inputs parameters. The first one called A, the second B, and C. A is of type S32, B is float32, and C is float32. So it's respecting what we had previously. That is to say that our first parameter was an array of integers. But then after adding some metadata to our inputs parameters at this level, it is invoking this fused computation here, and if you notice, it called it add multiply fusion, because after the XLA compiler analyzed our computation, it found that there is an opportunity to fuse operations. That's why here it's requiring the fusion of our operation. And if you look closely here, it says that it is calling this function here, fused computation, that has been defined at this level. And if you look at fused computation, the order of parameters also has been changed. That is to say that the first one is a floats, the second floats, and the last one is scalars, an array of scalars, sorry. So these ones correspond to the A inputs parameter. So the first operation is obviously the type conversion of param21, which corresponds to A, and then we perform the add operation, which will be stored here in the variable add0, and then add0 will later on be multiplied by param01, which is C, because if you look here, fusion is invoked with C as the first parameter, and here we are multiplying using param01. It may look as if a fusion was not performed given that we are using this intermediate variable, but this is just some high-level tracing. The fusion will be made while invoking the function. That way, no need to use an intermediate variable. And this is the main benefit of the XLA compiler. That is to say that it's analyze our computation graph, tries to find some places where fusion can be made in order to make computation faster. And that's why with JAX you can get performance boosts going from 2x, 3x, or even 100x. We never know. It only depends on what you are trying to do. Finally, let's try to have a look at a much more complex example to see how will the improvements can be quantified. That is to say, will the eager version perform on par with the compiled one, or will we get something impressive? To this end, we will define the very complex computation, let's say complex operation that performs a lot of computation just to put a lot of pressure on the memory. And then now we will create the jitted version using again JAX.jit. For our example, we will create an array containing 1 million elements and then reshape it to have the shape 1000 times 1000. And if you notice here, it's still using the same semantics as NumPy. That is to say that you can provide as many dimension size you want, and for a dimension to be inferred, I mean a dimension size to be inferred, you can just use -1, and then JAX will infer the size of this axis. And now, time for benchmarking. If we run the eager version, it takes around 10.8 milliseconds for our benchmark. And now we'll first compile our function, the first one, because one thing that I didn't mention is that the first time you call a jitted function, it will be compiled. Reason why the first invocation will be kind of slow, but the subsequent one will be really fast because the compiled assets will be reused in order to run this function. And if we benchmark the first one, we notice that it takes around half of the time of this initial function. That is to say that here, using JIT compilation, we have been able to get a 2x boost for our computation. So, therefore, as for this video, we are going to stop here for the time being. In the next video, I will give you much more details about the JIT compilation process. I mean, this video is just the first part, explaining how to use JIT. But in the second video, the upcoming one, we will try to see how to write much more complex operations using JIT compilations, because there are some gotchas that you have to be aware of. So that will be the main goal of the upcoming video. And as usual, let me know if you'd like me to develop a specific topic for you in the next one. See ya.